Welcome back. This video will be about dealing with negative logarithms, scenarios where you might have exponential decay, you might naturally have a base between 0 and 1. For this video I have this, let's see if we can see it, Jakar student log slide rule. It actually has log scales on the back and a sine scale, interestingly. But it's essentially a copy of a Aristo Scholar slide rule. The same layout as the Aristo Scholar. This log scale is across the top and is basically a slide rule designed for students. Okay, just as a reminder, if we have log of something like 4.1, that number is going to come out between 0 and 1, and we use that as the mantissa of the logarithm. Let's see if we can find it on here. Here's 4.1 on the D scale. And remember, usually with the log scale you can get a 3-place accuracy. So here I see 6, 1, and between mark for 2 and mark for 4, so 6, 1, 3 is how I'll record that logarithm. Now, we know that if you change from 4.1 to say 4.1 times 10 to the 5th, right, or 41 with then 4 zeros, then you can split the logarithm over multiplication into log of 4.1 plus log of 10 to the 5th, and of course since this log is base 10, this is a 5, and so this becomes 5.613. So that exponent there essentially becomes your integer part. If you had, say, 41, it would just be 1.613, 410, 2.613. So what if you go in the other direction? So here I have log of 0.41. That's the same as the log of 4.1 times 10 to the minus 1. So of course in the same way this should be a minus 1, or approximately minus 1 plus 0.613. Now that minus 1 plus 0.613 you can compute, and you'll get that that's negative 0.387. But it would be nice if there was an easier way. That subtraction could be prone to errors. So another way I'll suggest to do this is when you have the common log of some number which is between 0 and 1, what you do is you read the L scale backwards. So remember, the L scale runs from 0.0 to 1. What I like to do is take the tens complement of these major divisions. For example, 0.8 should be 0.2, 0.7 should be 0.3, 0.6 should be 0.4. So I would read this 0.7 as 0.4, or sorry, 0.3, and I imagine the scale runs backwards. So that if it runs backwards, that's 0.3, 5, 6, 7, 8, right? 0.38, and then I see mark there at 7. So I basically just, let's come off a little. You can see I read 0.387, and I know that it has to be negative because I took the log of a number between 0 and 1. Okay, now the question is, what would change if you want log of 0.041? Well, this is just subtracting another 1 from the logarithm, so this should be about negative 1.387. Okay. If you subtract another power of 10 by dividing by 10 again, then this should be negative 2.387 for the log of 0.0041. So one way to remember what this integer part should be for negative logarithms is it's the number of zeros between the decimal point and where your number starts here. So here is a 0, and here I have a 0 integer part. Then here I have a 1, and a 1 integer part, 2 integer part. And of course, if your number is greater than 1, then you're counting the number of digits to compute that integer part. Okay, so basically you need to count the number of zeros. Let's do an application. So a car depreciates from $4,030 to $3,150 over 13 months. What is it worth after 48 months? So I'm going to assume there's an exponential model. In other words, the amount I have is the initial amount times some base to power t. That base, of course, here is going to need to be between 0 and 1 because of the decay. Okay, so in other words, what I have is that 3150 was the original 4030 times some base to power 13. Okay, so that base should be, well, the 3150 over the 4030, and I need the 13th root. Let's write like that. Okay, then the amount, it's coming up here, the amount that I'm looking for after 48 should be like b, or initial amount, times b to the 48. And of course here that'll be 4030 times this, 3150 over 4030 to the 48 over 13. Okay, let's see how we would compute that. What I'll do is do this in the standard way by converting this to 10 to the something using the slide rule. So let's compute the 3150. So here's 315 on the D scale. Going to divide by 4030. So let's align that. Okay. Then I see that that is about 0.7 something. Okay. Sounds about right. Okay. So to compute what that exponent should be, I'm using the L scale on the top here. And of course, since that number is between 0 and 1 and not greater than 1, I'm reading this L scale backwards. So here I have 0.9, which I'm reading as 0.1. So 0.10 looks like 7. So negative 0.107. Again, because that was about 0.7, had a node zeros before the significant number. Okay. Now, of course, what I want to do then is to compute this as a power of 10. So I'm going to take that negative 0.107 and multiply by 48 over 13. Okay. So here I have 107. Let's divide by 13 using C and multiply by 48 coming out on C. Sorry, I have a new camera that might not be as good as the old camera at focusing. But what I can see here is I get about, that this is about 10 to the negative 0.394. I read it as 395 before. Let's go with that, negative 395. Okay, so what I need to do to compute this whole number is find 395 on the L scale. Okay, so for 395, again, because that's negative, I'm going to start at 7, which is 3, then 39, then 395 should be right in the middle there. Okay. And so I see on the D scale, this is going to be about 40-something%. So I'm going to take that and simply multiply by the 4030 to get my final answer. I'm going to use CI. Alright. Final answer is down here at the index. Looks like 162 and a hair. Let's just read it as 162. Okay. So this is about 162. And of course that's 1620. Okay. Alright, as a second example, we'll do a half-life problem, again, where we have exponential decay. We'll again assume exponential model. And so the half-life of carbon-14 is 5,730 years. If 3.6% is left, how old is the specimen? Assuming it starts at 100%. Then what I have is, well, the 0.36%, that's like this, is, I'm sorry. We need to start by using the half-life. Okay, you have 50% left when you have B to power 5730. Okay. So what is b? B should be 0.5 to the 1 over 5730. Then, okay, how old is the specimen? Let's see. Well, I have 0.036, 3.6% left. So let's see, that should be b to some power t. T is what I'm looking for. Of course, I could rewrite this using the above, 0.5 times to the power t over 5730. Okay, taking logarithm with base 0.5, I see that what I'm looking for, this, t over 5730, should be log with base 0.5 of 0.036. Okay, let's come over here. Oh, okay, I'll multiply both sides by the 5730. And instead of this, I'm going to use change of base, use the common log. Okay, and I'll get those numbers on the slide rule. Okay, first we need log of 0.036. Again, I see this 1 0 here, so this is going to be negative 1 point something. And let's see, here's 3, 6, and looking at the log, I read backwards, so 4, 4, 4. For log of 0.5, it's again negative. There's no 0 there. And I need the 5. Okay, so I see that that's 0.7, so I'm going to read that as 0.301. Okay, all there is left to do is multiply. So let's take 5, 6, 7, 3. About 573. Let's divide by the 301 using C. And then multiply by the 1444. Again on C there's 1, 4, 4, and about in the middle there, 4. And final result is on the D scale. It's about 2, 7, 2, 7, and looks like 5. And let's see, this is about 4, so 27500 years. Hope you enjoyed this video, and there should be more to come. Take care.